Welcome to linear algebra. This first day might be review for you, and if it is, fine. If it's not, that's fine too, okay? But I'm going to begin with the beginning so that we get a firm understanding to move ahead with the semester. So first of all, what's a linear equation? Well, generally, an equation and a function are two different things. An equation would be, for instance, setting a function equal to a number or setting two functions equal. Those would be equations. A linear equation, let's say in the variables x1, x2, x3 out to xn is an equation of the form, well, it looks like this: a1 x1 plus a2 x2 plus a3 x3 all the way out to an xn equals some b, okay, where a1, a2 out to an and b are real numbers. And these a1 through an are the coefficients of the equation. And the variables, as I mentioned, they are written at the top. They are x1 to xn. Okay, this is a linear equation. If you see squareds, or if you saw two things multiplied together, if you had a term that was x1 times x3, not linear, or if you had the cosine of some term, not linear, okay? Linear means you have the variables with the power 1 and then times some coefficient in front, added up like this. These are the linear equations. And then a linear system this is a collection of linear equations that have the same variables. x1, x2, out to xn, okay? Sometimes this is called a system of linear equations. And I will say right now, this linear systems or system of linear equations, same thing. This is the focus of this course. Okay, well, let's do some examples. Here are two linear systems we will begin with, and they're both just with two variables. So I'm going to do three of them with two variables, then I will do some that have three variables, and that's going to be the plan, okay? Well, how would we find a solution? So a solution to something like this would be, let's say x comma y, that satisfies both of these. Or maybe there's several x comma y that satisfies both of these. And how could we find this in a way that is like methodical? Because you will have even seen stuff like this in previous classes, and you just sort of do your best, right? But we will find a methodical way to solve so that we could, in theory, have a 7 by 7. We have 7 equations, 7 unknowns, and we could go through our methodical order of doing things, find the solution if there is one, or the multiple solutions if there happen to be multiple. Okay, so what could we do here, for example? Well, let's take, and you will see my notation as we do this, we are going to take this system and I'm going to multiply. One thing we can do with a big linear system is you can multiply one equation by a constant, add it to another. So what I'd like to do here is eliminate the x from the second equation. You notice if I do this, I will be able to solve for y. And then once I have y, well, you can go back up here and find x. This is the goal. Okay, and I mentioned you've probably done this before. Okay, well, I'm going to multiply. So I'm going to take -2 times the first line and add it to the second line. So here, my notation here, this is line 1, this is line 2, like this. Okay, well, what happens when I do this? I have not altered line 1. It's still x plus 3y is 1. Line 2, well, take -2 times this line, add it here. So the first equation is 0, and then I get -7. Y is -2 times this plus this, you get 7. Now, what's another thing you can do? Of course, in your mind you're thinking, okay, I see it. Y is -1, but I'm trying to teach the operations we can do. Well, from here, we can take, so one thing is you take a multiple of one line, add it to another. Another thing you could do is just multiply through by a whole line by a constant. So I will take -1/7 times L2. Okay, this is what I'm doing here. Then I get x plus 3y is 1, and I get y is -1. Okay, so far so good. And you notice by eliminating the x, this was our goal, we have, okay, solve for y. I could do the exact same type of operations, take a multiple of one line, add it to another. In this situation, I would be taking, I will move down here, I would be taking minus 3 L2, add it to L1, right? So what happened was that this line 2 remained this, and then when I take -3 here, we got x equals, these two will cancel, and then we get 4, okay? So the only thing I've done, I've multiplied through by a line by a constant, taken a multiple of one line, added it to another, and I have the solution. So we have the solution here. It is 4 comma -1. Okay, well, let's do the same thing here. In this example, again, it's a linear system. We have two variables. I'm going to do the exact same strategy where I take, let's see, I want to eliminate the x. Okay, so I'm going to take 2 times line 1, add it to line 2. My line 1 remains the same. It is x plus 3y is 1. Well, you notice my line 1 was the same in both of these. It's fine. They're just still two different examples. Now, what happens when you take 2 times this and add it to this? Well, I get 0, 0, 0. So I get 0 equals 0. Well, okay, what you see here is, in this example, we have infinitely many solutions. Maybe I'll write this below. We have infinitely many solutions. In fact, our solutions, you see, this is a line with slope -1/3, intercept 1/3, like this. And every single point on this line is a solution to this linear system. We have infinitely many. Okay, well, let's do one more quickly. Okay, here we go. We're going to take -2 L1, add it to L2. What happens? Line 1 remains the same. But then, here, 0, this adds 0. 0 is -2. That's never true, right? Never. What this says is we have no solutions. Now we have 3 equations, 3 unknowns, this linear system. One reason that I went slowly per se, through two equations and two unknowns was to get, as I mentioned, this method down. So, for example, what are we going to do? Well, I'm going to multiply, let's say, add a multiple of one row to another, or multiply one row through by a constant. But my strategy will be, first, I'm going to eliminate the x's in this row and this row, okay? And then I'll subsequently eliminate the y here. I will solve for z. And then I can sort of backtrack, solve for y, solve for x, like this. We will see, okay? And this is a methodical way, as I was saying. Of course, with two equations, two unknowns, sometimes you would just solve for y in terms of x, stick it in the second equation, right? And that works until you start having larger linear systems. So we are really focused on the steps. Okay, so here, what I mentioned I would do, we will eliminate the x in the second and third line. And just like we started last time when you sort of see the steps written out, let's see. This one will be L1, L2, L3. Okay, so the first thing I'm going to do is I'm going to do two things at the same time. First, I'm going to take negative 2L1, add it to L2. Negative 2L1 plus L2, and I will take, look, just minus L1 plus L3, okay? And then I will recopy what I get when I perform these operations. So I have the first line is still x plus y is 0, and then here I'm going to get 0, and then I will have, let's see, minus 3y plus 3z is 3. This is by doing this operation. And finally, when I take minus L1 plus L3, so I'm adding it to here, I get, well, this is 0. I get negative 3y minus z is 3. Okay? Now, as I mentioned, now I want to just look here. Now, well, this little piece, if you think about it, it's two equations, two unknowns, but I want to eliminate the y here. And so, maybe instead of going down, I will just move. It's difficult to do this on the board. I can't just keep going across forever, especially with this small board. But I'm going to come here, so when you read this, here's what I'll say, and I'll do this semester, because it's very likely I'm going to be recording on this small board in my home, right? We're going to read this way, and then we're going to come to the next line and read this way, and then we're going to come to the next line and read this way, okay? This is the order we should read the problems as I'm working them. Very nice. So what am I doing? I'm looking at the black system up there, and I'm just simply taking minus L2 plus L3. So I'm adding or subtracting L2 from L3. X plus y is 0. Then we recopy the second line. Minus 3y plus 3z is 3. And then we subtract line 2 from line 3. And we get, let's see, negative 4z equals 0. Okay. Technically, we could do the steps as we did when we had two equations in our linear system and two unknowns where, well, what can we do? Multiply a row by a constant, add a multiple of one row to another. So I would multiply, for instance, negative a fourth L3, and you see we solve for z. This line is the same, this one is still this, we get z is 0. And I could go through the steps of multiplying, what would I multiply? Minus 3 times this row added here. And then, and sort of working our way back up, which I'll do in the next one. It'll be a little more complicated, but this is fairly easy to solve. You see, we see z is 0. Once z is 0, step back to line number 2, and we get that y is negative 1. Once y is negative 1, step back to line number 1, and you get that x is 1. So you see here, we have a unique solution It is the point 1 minus 1, 0. We have exactly one solution to this linear system. Let's very carefully do this second example where we have a linear system with 3 unknowns and 3 equations. And all I'm going to do is multiply a constant times one line, add it to another, or multiply a constant times one line. This is all I will do, okay? So let's do this very carefully. Here we go. The first thing I'm going to do, just like in the last one, is I will eliminate both of these x's in line 2 and line 3. So this involves minus 2 line 1 plus line 2 and minus 3 line 1 plus line 3. And let's recopy the corresponding system. The first line has not changed. The second line is now, well, the x is not there. And then here we have 4 minus 2 gives me a 2y. And I have minus 3 minus 2 gives me minus 5z. This will be 1 minus 18, negative 17. Okay? Now we do this, right? We get 3 minus 3, eliminated the x. We have 6 minus 3, or 3y. We have minus 5 minus 3, negative 8z. And finally, we have 0 minus 27, negative 27. Okay, what comes next? Well, if you look at this, I'm going to put my arrow this way, but as I mentioned, I will continue on the second line. This is how we have to read with my small board. Okay, so what's going to happen next? I want to eliminate this y. This coefficient is 2. I will multiply the second line by negative, 3 over 2. So negative 3 over 2, L2, add that to L3. And here we go. Okay, here is where maybe I will, right here, right underneath this, maybe in blue so we can read it well, I will make a little fraction side work box. Fractions will take somebody down if you're not careful. It's very easy to make a mistake with fractions. So, okay, well, this is fine. We get minus 3 plus 3, there's 0y. But now, if we have minus 3 halves times minus 5, this will be a positive 15 halves z. And then with this line, minus 8z is a negative 16 halves. This is negative 1/2 z. Okay, I'll write it in a moment. Right now I'm just doing some fractions. Then if I take negative 3/2 times this number, I get, well, 17 times 3 is 51. So it's a positive 51 over 2. And I'm adding that to negative 27, which is negative 54 over 2. I get negative 3/2. So this is just my side work. With fractions, I will erase it when I need the space. Okay, so what's the result here? My first line remains the same. My second line, I also have not changed. Oops, z. And then my third line has become, well, I have the terms here, negative 1/2 z, and this is negative 3 over 2. Okay, and if all I do is multiply a constant times a line or add a constant of one line to another, at this point I will multiply through. Line 3 will be multiplied by 2. So I have x plus y plus z is 9. Here I have 2y minus 5z is negative 17. And here I get that z is 3. Okay, but as I mentioned at the start of this example, I will carefully, now, well, here goes my side work box. I will carefully go through this where all I do is multiply as I said, a constant by one line added to another like this, or just a constant by one line. So when I'm working backwards, you see I have z, I can solve for y. Once I have y and z, I can solve for x. But what I'll do is it's the same idea, but now I'm going to work up and eliminate the z's in both of these lines. So what does that amount to? Well, I'm going to take 5 times line 3 and add it to line 2. That will get rid of this z, and then, or this z term, I should say, and then I will take minus line 3 and add it to line 1. Add it to line 1. Okay, so now let's write what results. We have x plus y equals 6. And then here we get 2y equals, well, you take minus 5, positive 5 times this is 15, minus 17 plus 15 minus 2. Now you see this is looking great. Now I'm going to continue this pattern, as I mentioned very carefully. The next thing I will do is multiply through line 2 by negative, or positive a half, excuse me. So I take 1/2 line 2. My first line I have not changed. X plus y is 6, but I get y is -1. And then this very last step, what is it that I want to do? Well, I want to take minus line 2 and add it to line 1. Okay, so here we go. This would give us x equals 7. Now, technically, I didn't copy the whole system every time. We still have z equals 3 here, z equals 3 here, and we would have y is -1 and z equals 3, right? I should have kept copying that each time, for example, but now we have the unique solution. So the unique solution here, it was the only solution that we got, was this 0.7 comma -1, 3. So we have one solution to this system. But one thing I like about the way that we did this, it was very methodical, and this was my point, where we could have followed these same rules and done, say, a 30 by 30, where we have 30 linear equations and 30 unknowns. Well, not on this little bitty board, but in principle, where you eliminate everything under here, and then you keep the y, eliminate under here. Then you would keep this one, eliminate, keep this one, eliminate, until you get down to the bottom, and then you just work backwards. You eliminate above, eliminate above, eliminate above, like this. We are going to be using this a lot more, this type of elimination, throughout the semester. We will just get into the language of matrices, which I think makes it a little bit, maybe a little bit easier than writing out the equations every time. Okay, well, but before we do any of that, we're still in our introduction to linear systems discussion and section. I would like to do 2 more examples to see what other types of behavior can happen when you have, for instance, 3 equations, 3 unknowns, and then we will look at the pictures to understand these linear systems geometrically, say, at least begin to understand them. So let's look at 2 more. Maybe I will draw a line right here. Well, let's begin as we have in the other 2 examples. These will be different though. The last 2 examples, we had a unique solution to each linear system. Here, let's begin. If we try to eliminate the x, well, we already have no x in the second equation. Eliminating the x here, we would take negative L1, add it to L3, right? And what do we get if we then write the result? We have x plus y plus z is 2. We have y plus z is 1. And in the third line, we have we just subtract. Oh, we have y plus z is 1. Okay, well, I'll make a comment about that in a second. Now let's do the same thing for this example, okay? I'm purposefully sort of treating these together. Well, this example, in a way, is handed to us. This is like example 1, and this is example 2. It's already handed to us where the x is eliminated in the first two equations. So I would just work to eliminate the y in this third equation, which would be, here we could just take negative 2 L2 added to L3. Okay, great. Let's write down what results. We have x plus y plus z is 2. We have y plus z is 1. But then, if you add negative 2 times this plus this, we get 0 is negative 2. Okay, well, these are both similar to phenomena that we saw with two equations and two unknowns. Look, here it's really just two things. In fact, I could take, let's even do another step if we want to, for completeness. I could take minus L2, add it to L3. And then we see even more clearly what's happening. We have x plus y plus z is 2. We have y plus z is 1. And then here we have 0 is 0. So now these match up almost the same, except in example 2, this equation is not true. This equation says no solutions. So we have no solutions here. And up here, well, there's going to be infinitely many solutions. How could you find some? Well, let's just say for a moment, how could we find infinitely many? Okay, very nice. Let's say that z is t, or t can be any real number. Okay, well then, solve. Y would be 1 minus t, right? Now, if y plus z is 1, that means this sum is 1. Subtract here, x equals 1. No matter what y and z are, provided y plus z is 1, right? So if you solve both of these, so here, 1 minus t, for t in R, this was our real numbers thing, is a solution. This is infinitely many. Every real number t corresponds to one solution like this. We have infinitely many, and this will be, as we will see in our pictures, this will be a line.
Well, what I'd like to do is spend a few minutes going over graphically or geometrically what can happen with these linear systems, and I will start with the first few examples that we saw, which were just two equations and two unknowns. And the first one we saw was here, x plus 3y is 1 and 2x minus y is 9. And we found that there was this unique solution, and you can see it here. Each one of these linear equations defines a line in the plane, and they intersect. Well, you can't see my hands because of my background. It's Northeastern. Okay, they intersect at this 1 point, 4 comma minus 1, which we calculated. This is one way that lines can intersect in the plane. However, now let me take off this. If we took, for example, we have these two, x plus 3y is 1 and minus 2x minus 6y is minus 2. Oh, take that label. But you see here, these are the exact same line. We had infinitely many solutions. Well, it's just two overlapping lines. The whole line worth of solutions is our solution set. Okay. But then finally, we have this third And you see the problem here. These are two lines in the plane, but they're parallel and they never intersect. These were the two that I had no solutions when I tried to solve the linear system, which was this first equation here and then the third equation below. Okay, so this is in the plane. Two equations, two unknowns. We plot lines in the plane. Let us start by just looking at, so you see what I have here. The very first line I have just graphed, and this wasn't one of the examples we did, but I'm just showing geometrically what is one equation, one linear equation with three variables. So what I have is x plus 2y, x plus y plus 2z equals 0. And I have this graph, and it's in red. You see here, this is a plane in R3. Okay, so this is general. If you have a linear equation with three unknowns, it's a plane like this. Well, now let's start looking at geometrically the solutions to three equations with three unknowns, linear equations, of course. This is the very first one we did. X plus y is 0. 2x minus y plus 3z is 3, and then x minus 2y minus z is 3. Okay, we found it had a unique solution. How do you see that geometrically? And it is right here. It's quite beautiful. What do we see? Well, each plane is colored with a different color. So the solutions to just one linear equation, as I mentioned, it's a plane. Each one is a different color. And if you are a solution to all three, it's the intersection. Just like for 2, we looked at the intersection of two lines. But here, if you take three planes and you intersect them, if you can see in this picture, what you are getting is a single point. The intersection of all three planes is a single point. This is when we had a unique solution. This was our very first example. Now, let's move down. The second example was also a unique solution. I won't look at that. Let's look at the third and the fourth. In the third, we had a whole line worth of solutions. Now let me, okay, we can see it pretty well here. Do you see this? What's happening is, looks kind of like a book that's open with the pages coming down. But you see these three planes, they share a line in common. You see it, right? It's very pretty. This is one way planes can intersect. So you can, and these are distinct planes. You could also have just two planes that are identical and then a third cutting them, something like this. Or you could have all three planes identical. I guess in that case, you would have a whole plane's worth of solutions. But here, we have three different planes. Their intersection is a line, as we see in this picture. And then finally, we did one where we had no solutions. Let me see if I can get a good angle here. Oh, something like this. Two of the planes in this case are parallel. Okay, and then this third cuts through them both, but common to all three, there's no intersection. Okay, when we tried to solve, we got like 0 was equal to some non-zero number. And of course, that means we have no solutions. So this is geometrically, well, this is another way that planes can intersect, as we see looking at this picture.
Let's close with this example. And it's a little bit different, but it's a nice application of a linear system. We want to find all polynomials. Maybe I should write that f of t is the form a plus bt plus ct squared, like this. We want to find, well, this is a general polynomial of degree less than or equal to 2. And then we have this information. The graph needs to go through this point, and then we know something about the derivative. Well, first of all, what this is going to lead to, I should say, we will have a linear system involving A, B, and C, and then we will solve this linear system. Okay, well, what we know is that f of 1 should be 3. So 3 should be A plus B plus C. That's evaluating at 1. And then, right, maybe I should make this observation here. This says f of 1 equals 3, and this says f of 2 equals 6, right? If the point 1, 3 is on the graph, then f of 1 is 3, like this. Or if 2, 6 is on the graph, f of 2 is 6. Okay, we have that down. And then, now let's get the second equation. F of 2 is 6, says 6 is, evaluate at 2, a plus 2b plus 4c. So far, so good. Well, there's this third equation about the derivative. This is the derivative. The derivative at 1 should be 1. So here, maybe I should come over here and take the derivative. Okay, so if this is my function, then f prime of t, well, this is polynomial. It's b plus 2ct. Okay, now evaluate this at 1. This is going to give our third equation. Evaluate that at 1. We should have f prime of 1 is 1. So 1 equals, well, it's going to be 0a, and then we will have b plus 2c. Okay. Well, the only difference is instead of having x, y, and z, I have a, b, and c. And then I've put the constant parts on the left-hand side versus the right-hand side. This is the only thing that's changed, but it's exactly the same as we have been working with. Okay, so what am I going to do? Well, first, I want to eliminate the a. So I will take, again, this will be line 1, line 2, line 3, okay? So I'm going to take, let's see, minus 1, line 1, add it to line 2. Okay? And maybe, just I guess, so that it matches, I'm going to put the 3, 6, and 1 on the other side of the equal so that it matches exactly what we were doing before. Maybe I should. Okay. But this was sort of the new part, the setup. So we have, oh, I said I was going to put it on the other side. We have a plus b plus c is 3. And then we are going to have, let's see, this minus this, b, this minus this, plus 3c is, 6 minus 3. Oh, it's another 3. Okay, then we just recopy b plus 2c is 1. I hope this is making sense. This is the hard part about doing my lectures this way. I can't, hey, is everybody okay? Well, I am in my bedroom right now. There's nobody in here but me. Okay, well, we will make it through the semester. Okay, now we want to eliminate this b so that we are able to solve for c. This will be, we will take negative line 2, add it to line 3. Very nice. A plus b plus c is 3. Then we have, this remains, b plus 3c is 3. We take negative this, add it to this, which becomes negative c is negative 2. Okay, so, well, technically, what are we doing next? We're multiplying minus 1 times line 3. Maybe I'll do this little here, minus line 3. And I'll just recopy it and move directly into the next step. So this would be a plus b plus c is 3. b plus 3c is 3. c is 2. What am I going to do? I'm going to take minus 3, line 3, add it to line 2. Just take minus line 3, add it to line 1. We're almost there. So line 1 becomes a plus b is 3 minus 2, which is 1. Line 2 becomes b. So I have minus 3. Oh, this is going to be 3 minus 6. This will be negative 3. And then this is still C is 2. Okay, so we have B is minus 3, C is minus 2, and one more step. All we need to do is our final step is just take negative line 2, add it to line 1. And then we get A is 4, B is negative 3, C is 2. So our polynomial, now we're ready to have our final answer. Maybe I will, don't know where to write it. I'll just put it here. Oh. Okay, we solved. A is 4. B is minus 3. C is 2. Find all polynomials. Well, look, there is a unique. The answer is there is just one. And here it is. Okay? Very nice.